Okay, fine. All right, so yeah, hi everyone. Thanks for coming here. So I will basically follow up a bit on the keynote and just talk about what happened in DFTK, the density functional theory package that I mentioned at this lower left level of this basically high accuracy quantum chemical simulation. And in particular, what I want to talk about is some of the things we did on the direction of algorithms and the direction of error control, and also basically trying to combine communities. And I will show you a little bit how to actually use the code in practice. So I think from the motivation, I'm just showing this as a reminder slide to get it all back in your brains, in the active part of your brains. We need new materials, because materials is basically what limits the solutions we have to problems like climate change, energy, and so on. So as Rachel has pointed out on Wednesday, what we're doing is we're actually running quite a bit of computations. We're really simulating, for example, how such a silicon crystal behaves from the quantum mechanical point of view in order to understand, is it useful for solar cells? Is it useful for other technical applications? And as we have pointed out, this is something that we don't just do 10 calculations on. Really, we're more doing a few thousand, maybe tens of thousands of calculations. We're really like, for example, on this Archer 2 figure that we also had on our previous presentation, we really occupy something like 50% of standard academic computers with these kind of simulations, right? So this is stuff that people really do, and this is things where, certain questions now pop up that haven't really been part of this field beforehand. So just to give you some ideas, in particular, it's a question of complexity. So we started looking into this a little bit in the keynote. There's really a lot of different steps that one has to go through. First, generate the data, train some surrogates, for example. And basically, all of these steps have really a lot of parameters, right? So we're talking about things like tolerances, which algorithms do you actually choose in order to really run the simulation, which model, and basically all of these choices need to be made automatically now that we're running tens of thousands of calculations. And if I make a wrong choice, then potentially I get a wrong answer. So this is actually a non-trivial problem, and this is why people have developed actually these kind of workflow engines that I show here at the top that automate using heuristic choices the setup of these kind of simulations. But of course, this is not perfect, and in particular at the level of really running tens of thousands, hundreds of thousands of simulations, sometimes these heuristical setups go wrong, and then simulations basically need to be repeated. Again, typically this is done heuristically, but the key point I want to get across is every simulation that you have to repeat is wasting resources, and supercomputing is also not cheap, right, in terms of energy and of course also, therefore, from the climate point of view, it has an imprint. And humans typically do this checking, not always, but oftentimes. So basically, it often is in these workflows now the human factor that limits the overall throughput. So if we can make simulations effectively more autark, we can make them more robust and more efficient, we're saving not only on energy, but we also make it faster to develop and discover new materials. So our mathematical questions, so to speak, are how do we optimize properties, how much accuracy do we need, and can we use tools such as algorithmic differentiation to go through these things faster? Okay, and here this is just the math slide, right? So don't look at all the details and get scared. The key point to get across is that in this kind of density functional theory simulation that I'm running, that we are running in our code, we have a complicated minimization problem. So we basically minimize some energy functional over, actually, it turns out, a Riemannian manifold. So this is not even Euclidean space. So we have basically a manifold optimization problem, nonlinear, non-convex, right? So basically, it's a complicated problem. That's what I want to try to say. And now just to give you the idea of what are the kind of research questions we're interested in, I'm actually going to focus on a slightly simpler model problem. And so the typical numerical analysis point of view, when you have such a minimization problem, what you're interested in is, for example, you want to come up with like fixed point methods. So in DFT, that would be the so-called self-consistent field approach. Maybe some of you know this. And there, what the key point is that the convergence of this guy actually depends on the second derivative of the energy, effectively. Now, other things that people are interested in is properties and response. So I will talk about this a bit more, but the point is that this connects to physics. And in order to do that, it actually turns out that, again, the gradient of the energy and the second derivative of the energy pop up. And similarly, in fact, if I want to do numerical analysis and I want to understand what is the discretization error, for example, in my computation, then again the same structure pops up. So I have to invert a second derivative of the energy and multiply it with the first derivative of the energy, right? So the key point to get across here is that this energy functional, its first and second derivative, these are like the key ingredients to the kind of simulation software from a mathematical point of view that I need to understand. Okay? So that's sort of the mathematical structure. Now let's talk a bit about actually getting this to work in the context of a real quantum chemical simulation. The problem is that there's a clash of many aspects, such as community, conventions, language barriers, and so on, right? So I used here a very mathematical language. That's not something that is extremely familiar to people who come more from the application side. And in particular, in the applications, if you spend, like you do in math, basically a year or a year and a half on a paper, that's not going to work on a collaboration, right? Because people who do simulations want to be much faster. So therefore, we have basically problems that are social problems that cement in software, right? Because how you think about your research affects how you write your software. And in the end, as a result of this, these kind of mathematical structures that I have just alluded to, they're really not that exposed in existing codes. And however, on the other hand, mathematical codes that do expose the structure, they tend to be really slow and don't work so well in practical context. And here, same as I said in the keynote, I think if we can come up with software that allows these different viewpoints to compose in one code, that actually allows us to actually also compose these different fields and come up with joint academic research. And that's really been ultimately the motivation for the density functional toolkit, to make something that is accessible to different communities, to be able to treat like really model problems that are interesting from a math point of view, but also to go to something like 1,000 electrons, that's like a realistic scale system, and all of this in something like 8,000 lines of code, which is really, really small compared to what standard codes in the fields have. More recently, we integrated also, or start to integrate into high throughput. So the plan is that maybe over the next half a year or so, we are actually able to use our code really to run tens of thousands simulation on one of these existing state-of-the-art frameworks. We do standard integration with Julia things are listed here. And in the end, there's really been, I mean, to sort of prove the point here, that we have really a number of contributors from different fields on GitHub that contributed features, and some undergrads that did various kinds of work and really managed to push the state of the art of the code. All right, so some things that we did in research from a research point of view. So for example, we looked exactly at this gradient is equal to 0 problem, the self-consistent field problem. And the point there is that the parameters to choose is, in your iterative scheme, what is this p minus 1, the so-called preconditioner that accelerates your convergence? What's the step size, this alpha? And basically, this is exactly what these kind of parameters that are typically chosen by trial and error. However, now what we have come up with based on some mathematical insight is essentially algorithms that automatically look at the system that you have and basically based on the information you acquire while you're running the simulation, chooses automatically this preconditioning step in a system adapted way, such that we overall are able to perform much faster algorithms than state-of-the-art codes. So maybe our code is not as fast as state-of-the-art. However, we, for example, here win a factor of 2 just by being smarter about the way we solve the problem. Similarly, here we have a setup that automatically determines the damping factor, which in existing codes is often something where people really need to fiddle around until they find the right damping for systems to work. And we can actually determine this automatically using a mathematically proven algorithm. Similarly, things we looked at in more recent times is look at properties. So energies are great, but in the end, it's really the change of the energy when you change an external parameter that essentially probes experimental quantities of interest. And here, when you look at this from sort of the algorithmic point of view, what it is at this self-consistent field, so this sort of gradient equal to 0 problem, that gives you a so-called fixed point. And then if you want to understand how this fixed point changes when you change the external parameters, so when you perform an experiment, this then leads to an implicit function, and therefore you can use AD, implicit function theorem, to compute these things. And that's exactly what we're doing, and the type of properties you can get with this framework is, more or less standard properties of the field: forces, dipole moment, elasticity, spectra, various things like this. So this is things people are actually interested in practice. The nice thing about basically doing this with an AD framework is that you can also compute other derivatives, so things that are usually not so available, such as sensitivities or surrogates. And just to give you one other idea how we use AD in practice, here that's a quantity called the stress. That's something where you also need to compute a derivative of the energy, in this case with respect to the lattice setup. And here it's the code, and this is the code, and this is the equation. And you see it's very much one-to-one. And I'm not actually cheating here, so if you want to take a look, this link here brings you to the code that we have live, and you will see it's basically this plus a bit of sugar around it. So this is how we do the computation. We really implement the physics. And just to give you an idea, that's 20 lines for us. Other established codes use something like 1,700 lines, simply because they hand optimize and hand implement these derivatives where we use AD. That's something that Niklas, who has fortunately joined my group a few months ago, has done in a GSOC project in 10 weeks. The basics of this, now we've improved this, but you see that the high productivity is also exemplified in this example. Talking more about performance, we've worked a lot on basically making this AD framework fast in the past years. For example, really by looking at the system of equations one has to solve in order to get the implicit differentiation going. And there it turns out it's again a nested problem. You have to avert a complicated operator. And this chi0 term here that you have to iteratively apply in order to do the inversion itself also is an iterative problem, right? So you have two nested set of iterative loops. And it turns out that this inner thing can actually be ill-conditioned, in particular for metals. So you see it really needs a lot of iterations. So here, this is the number of iterations over basically the kinds of equations you have to solve. And we've worked on methods, for example, that use the structure, the mathematical structure of these kind of problems to, again, 40% reduce the iterations. So again, something where using Julia, where algorithms are accessible, helps you to accelerate, not necessarily by using HPC type of acceleration, but to understand more about your problem. Another thing I wanted to quickly get into is error control. So if we understand errors along different axes of research, for example, here I'm representing it by different basically resolution and different color. If you basically only are interested in this kind of resolution, you don't need to go to very accurate numerics, for example, to go to very high resolution in the color. Sometimes it's sort of okay to just find some balance in between. But to find the ideal balance, to find the ideal compromise between color and resolution, we need error indicators. We need to understand how much error does actually get induced if I'm sort of cutting down on this or that axis. And this is exactly where, again, mathematics can really make a contribution in order to understand what is the discretization error, what is the error of the model that I'm using here. And here again, we've been at the forefront at trying this in the context of plane wave density functional theory. We've come up in simplified models in so-called band structure plots. That's a very important quantity in this field, where basically you have error bars that indicate you the complete error within the model. So that is basically the chosen basis set size, the chosen numerical tolerances, and so on. All of this is in this mathematically guaranteed error bar. Or, for example, more recently, we are looking at more realistic properties, such as the density or really the force in a DFT computation. We're trying to estimate there the errors that come from the chosen basis set size. And the idea, of course, is to push this forward into the machine learning in the future and try to basically use this to balance errors along a larger material science pipeline. We've verified our code, again, using this high-throughput framework that I was mentioning. So this was done using automated calculations. And here we're testing some standard structures that probe sort of the physics. And you see our code agrees very well. So blue means good agreement with Quantum Espresso, one of the standard codes of the field. So we are now fairly confident that we're really reproducing the results of other codes rather well, and that the code is ready to be used in practice. All right, how much time do I have left?
We have 4 minutes left.
Okay, that's less than I expected, but at least I want to show you something. Oops.
I'm also allowing some time for questions. You can cut time from your questions.
Yes. Okay, so I have a notebook which shows some things. So one thing I wanted to at least briefly mention here is if, for example, you want to play with the code, in particular you want to try new algorithms, it's actually fairly simple. So here what I'm doing is I'm actually coding up one of these fixed point algorithms. And what you can do in DFTK is when you're actually running your computation, you can easily just slice in this fixed point algorithm. So for example, this allows me in a Pluto notebook environment to easily tune parameters of the algorithm and directly see what is the effect of actually running, in this case, a realistic system, right? So this is a system of silicon, so a non-trivial system that I'm computing. Similarly, we made GPU support in the sense that you can very easily just do all of this interactively on the GPU. Talking about AD integration, if you have, for example, the computation of a complicated quantity of interest, such as the band gap of silicon, so this is just some code that essentially computes the band gap of silicon doing a DFT simulation. Using ForwardDiff, you can now basically just say, okay, compute me the derivative of the band gap with respect, for example, the lattice parameter, so the one structural parameter of your problem. And again, it will do the SCF, it will call the AD, it will solve the appropriate underlying response problem, and directly give you the answer. As you can believe, we have some nice integration with JuliaMol-Sim, but also we can integrate into external packages such as Optim. Feel free to look at this in more detail and ask me for questions if you're interested. All right, so now I'm going to quickly conclude. So as you've seen in the keynote, I have an open postdoc. If you're interested, please contact me. We have a nice workshop coming up in Lausanne in November. There's some people in the audience here already have gladly confirmed to come. Others, if you're interested, please apply. And basically, I think that brings me to the end. I showed you a little bit the motivation and what we're able to do in DFTK at the moment. In the future, we will really want to work on this error control and sensitivity aspect enabled by AD and the numerical algorithms. And we basically want to use this for inverse design, for improving things in surrogates. And we currently also work in the other direction, integrating domain-specific libraries for HPC in the DFT context. There's a library called Sirius that is also developed in Switzerland. We're trying to sort of make DFTK a front end for that, because the current front end they use is in Fortran, and they don't like this. So we are offering to bring it to the Julia world. We're working on increasing composability with JuliaMol-Sim, and again, we're working on a tighter integration with this AIDA high-throughput workflow, such that our basically algorithms can be directly tested in a real practical context, and we can see if we bring some advantages here. There are some things where you can help. Performance is a big deal, especially if you're a GPU person. I really would like to talk to you. Parallelization, there's some low-hanging fruits where we want to work on. Some AD backends like Enzyme, I think, would also be really beneficial for us, but I simply don't have the time, or we simply don't have the time to work on this. So if you're interested, please let us know. Use the code and let us know if things don't work. I'm sure some things don't work, so please let us know if that happens. With that, I want to thank basically the people from my group, the people at EPFL I'm working with to integrate with AIDA, the various people from the math side I worked with over the years to make these algorithms happen, all over 40 contributors we've had over the past 5 years. And with that, I look forward to your questions.
So, someone has a question. Questions? You.
What happened with lutetium on the error plots? It seemed to be the only one where the simulations didn't agree.
If you have the answer to that, I would be very happy. So the honest. Okay, so I give you the 1 minute answer now, and we can chat about this for half an hour later. So the problem is, while we were doing this, we actually discovered problems in Quantum Espresso. Okay, so or rather in the pseudo-potential file format that Quantum Espresso uses. So because we were not making some approximations that they were implicitly making, and then we had discrepancies. So basically by this comparison, we noted that there was some issue in the way quantum espresso and this file format deals with it. So right now we're not sure if this is us or if this is them. So I don't have an answer to that, right? But it's a good question. I don't know.
Thanks for the talk. I wanted to ask about this computation of the second derivatives of the potential energy, particularly the algorithm that you implemented for estimating the preconditioning matrix.
This one.
Yeah, could you talk more about the method?
Yeah. Okay, so the math point of view is that the second derivative of the energy actually turns out to be this guy. Okay? And so what we are doing is, instead of inverting this exactly, we make an approximation for this chi0, which turns out to be the expensive object. And the approximation we use comes from homogenization theory. So we do a so-called row-sum mass lumping. We take this thing, which is basically a matrix, and we integrate everything on the diagonal. And from a physical point of view, what you get is the so-called local density of states. So it's actually really funny that a mathematical procedure turns out to give a physical quantity. So the point is that this local density of states turns out to be relatively cheap to compute and a good approximation for this chi0. So what we're doing is that we're just inverting this operator here once we have done one step of the self-consistent field. And we don't use the exact chi0, but we use this local density of states approximation. And this turns out to be able to really distinguish where is a metal and where is an insulator in your system automatically, and therefore it automatically uses the right kind of preconditioning for these kind of systems without you doing anything. Yeah.
More questions?
So you were showing these band gaps that you compute and the error bars that you are able to, and I was wondering, like, people use these GW methods for band gap calculations, and does this get you closer to?
Yeah. So I glossed over the details there in this paper, but this is actually not even DFT. So this is a so-called linear Hamiltonian, right? So this is a very simple model which is very wrong. So the goal here was to classify all the numerical errors. So floating point precision, the eigensolver tolerances, and the discretization error, and forget about the model error, right? So I can't answer this question because we actually didn't investigate it here. We just assumed that this model was ground truth, which we knew is not true, but we at least dealt with all the other things, right? So capturing model error is really tricky. Niklas works on one aspect of that, but it's really an open problem how to do that properly. Yeah.
Okay, thanks.
Well, actually, I have a question.
Yes.
So I saw that you have an algorithm to determine the damping constant. I was also always like twiddling with it. Now I'm curious how that works.
The way this works is essentially by this realization here. So essentially here we have a simplified version of the SCF, and we also have a damping parameter here. And now when we do one step, so we want to go to xk plus 1 starting at xk, we now ask ourselves the question, how large at this particular step should we choose alpha? However, since we know that overall this is a minimization problem, we can just do a line search along the direction given by the gradient and find the point which is lowest in energy. Okay? So far, so trivial. The problem, though, is that computing the gradient and the second derivative, which is what you would need to do this line search properly, is quite expensive. So we have some tricks to basically shuffle terms around such that the things you compute are the things you anyway need in the next SCF step, such that we can basically do like recycling of the computation that we have done before. So effectively what this means is that in this setup, one SCF step is as expensive as the number of line search steps you need. So typically we need 1 or 2. So it means that the SCF steps are usually exactly as expensive as they would be in a standard algorithm, or at most twice as expensive. Right? So it can happen that one step is more expensive, but at least for very complicated systems, such that this Heusler alloy you don't need to fiddle so much with the damping, because as you see, it actually automatically goes up and down quite a bit. Yeah. But again, in the paper are the details, and I'm happy to give you more of them. But this is like the high-level summary.
Okay, thanks. More question?
Thank you. So, I mean, I know the focus is a bit different than most like quantum chemistry packages that we have, but you've shown like how much shorter your code is in comparison, and then how good the element description or whatever you benchmark there was.
Yep.
Did you also look at speed for some like molecular systems? Like,
well, molecular systems in plane waves are generally bad, right? So the answer is we're going to be as bad as all the other codes. Yeah. So that's the short answer I can give for molecular systems. You can do it, but I mean you have to put a vacuum around it, and that makes you pay, right? There's some tricks in the literature. There are some tricks you can play, especially when you have surfaces, where sort of half of it is vacuum, but we haven't implemented those. Yeah.
I really liked how you can play with the code in the Pluto notebooks. Really.
Yes, so do I. It's great for teaching too.
Actually have one more. So
sure.
So you talk about preconditioners, and I always have a struggle finding a preconditioner works for my systems. How do you go around finding which one works for you?
So in this case, I use maths, and then I know that basically this approximation is sound, and so that this has the ability to capture the majority of systems. But I didn't show this, but one thing we can actually do in DFTK is we can build the iteration matrix corresponding to this SCF with and without preconditioning. And so then I can actually look at the eigenvalues of this matrix using Krylov-Kit, for example, because all of these objects are available as simple functions or operators, and you can use them interactively composing with other Julia tools. And then I can actually look at the spectral properties of my SCF. And then I can actually see, okay, with this setup and this preconditioner, my spectral properties are better, right? So I mean, of course, in general, when I do production calculations, I just use whatever setup and run the calculation. But for the debugging here, to make sort of this development, I can actually reduce my system, go to 1D, make it simple, and use Julia tools to really query the mathematical properties of my SCF, and in this case, sort of design the preconditioner such that it sort of fits the system under study. Yeah, that's sort of the big advantage of this package over existing codes, really, to have this simple playtesting and scaling up to a realistic setting where you can do real calculation.
It would be great if you have some sort of guide or tutorial on how to do that. I will be interested in that.
I think we have exactly that aspect as an example on the website.
Okay,
this dielectric matrix diagonalization. Yeah.
Okay, thank you. More questions? No? If not, then I would like to thank our speaker. And then we can have lunch.